Welcome everyone. This is the last lecture of the course, the short course, representation of compact groups. And today we are okay. So as usual, we begin with a summary of what we seen last time. So the last time we saw, try to recall them. So we pick a representation, B pi of a compact group. An invariant subset is a subspace of the slash of any element in G. Okay. So when we apply the transformation pi of x to U, it lies inside U. So we say that a representation is irreducible if it contains invariant subspace. So this is 0 and everything. A representation is called unitary if there is an either product such that the action of the element are given by representations, by unitary linear maps, sorry. And what do we mean by is G invariant in the sense that if we act on the element on the vector, and then we take the inner product, not acting with what happens, we call that the representation is unitary. A morphism between two representations or an intertwiner is a linear map that commutes with the action of G, and we say this in this terminology like this, is that any linear representation, finite dimensional linear representation, admits an inner product that is G invariant. So any representation is unitary. Yes. So we're going to talk about from now on only about unitary representation because any representation is unitary. And we can do that with having. So here we use the existence as a consequence of having this G invariant in a product is that we can decompose any representation into a sum of irreducible. So any representation can be decomposed into a direct sum of irreducible sub-representations. So to understand the representation of a compact group, we need only to understand the irreducible ones, okay? Now we are going to detect when a representation is irreducible or not, okay? So in this sense, we started by looking at irreducible representations. The first result about irreducible representation was the Schur lemma. And the Schur lemma have a joiner two irreducible representations, then in options. The intertwiner is 0 or it is an isomorphism or an equivalence, okay? And if so, any an endomorphism of it's given by a multiple of the identity. Yeah, I'm going to use that. Okay, so now we look at the functions on the group, and every time we have an integral in the continuous functions, we can take as usual, the inner product between functions, continuous functions, and we define it as usual as the integral of f, the inner product of two functions, between two functions, is the integral of the one function times the conjugate of the other one. This defines an inner product on the set of continuous functions. So we can to use to understand the function in the group, going to use the we extend the notion of following sense, we take two elements of a unitary representation. Just recall that now we are going to talk about unitary representations. If you take two elements of the representation, then we can define a map. The map that goes from G to C, the continuous map, which is given by in X, is given by the inner product of X acting on one vector times the other. So in short notation is this one. So if given two vectors, we can define a map from G to C, okay? Now, with all that we know about representations, we are going to show the following things. If we take two non-isomorphic irreducible representations, then these matrix coefficients that we define above satisfy the following. They are orthogonal with respect to each other if the representations are non-isomorphic. Yeah. And if we take the same representations, okay, so is the formula involves the inner product between the vectors that we choose to define the matrix coefficient. So how do we prove that? So let's prove that. So we see some calculations, okay? Okay, so the product is given by a trig. So what's the trig in here? So the trig works as follows. Just let's pick any linear map. So let T from W to V be a linear map. Okay, so if it is the only linear map, we don't know if this map is an incentrion or not. So we don't know if this map commutes with the action of G or not. So to produce a new map that is also linear map, but commutes with the action of the group, we take the average, yes, with the group G. How do we do that? We use the Haar measure. So let's say that a priori, today is Friday, I write in the wrong order. A priori, we do not know if T is an intentoiner. So we define another linear map by taking the average, a kind of average, by taking the sum. So we define T tilde to be in this new map given by the integral of our function T, but say that, but say conjugated by the action of x. Of course, when we conjugate by the action of x, then we have to put in the corresponding representations on each side, okay? And the first thing is we are taking the integral over something that is not a function on the complex numbers. It's a function that lies in V. So we understand this integral as, so we take a basis, and this integral is in each component of the basis, in each coordinate, is an integral of a function over C. So it is actually an integral by entry. So we can still do the integral. So it's like a matrix integral, okay? So we understand this integral like this. Okay, so why this integral is an intertwiner? So let's prove that. So let's take a y in G. So let's prove that it is an intertwiner. So let's compute py t tilde rho y minus 1. And this is by definition rho x minus 1 rho y minus 1 dx. And this is pi of yx t rho of yx minus 1 differential x. And what we saw about the Haar measure, that it is invariant with respect to translations. So this is actually given us the same as p of x t rho of x minus 1. So it's actually, this one is t tilde, okay? So it is, so what do we know is that t tilde is an intertwiner. So we go up and say, okay, it is an intertwiner between two representations. These representations which are isomorphic and non-isomorphic. So we have by Schur lemma that this T is 0 or an isomorphism. But if they are not isomorphic, then we know that by Schur that T tilde has to be 0. Okay? So if T tilde is 0, what do we have is that the inner product of T tilde of some W times V is 0 for all W in W and for all V in V. Okay? And this works for any linear map T. So now we're going to pick a specific linear map T. So the one given by an inner product. So I'm going to use the same letters as in the lemma. So let's take a V2 in V, a W1 in W. So for these ones, we define the linear map T that goes from W to V by T of some W2 is, we take the inner product of W2 times W1 and multiply it by V2. And this is for any W2 in W. Okay, this is a linear map. So we apply what we got before with this linear map. So we know that 0 is actually T tilde of W2 times V1. So, okay. wait a second, there is some question. Yes, the new linear map has the same. No, I call it T tilde. What do you mean by the new linear map? The new linear map is the one that I fixed, that I take T, the one given by the inner product. So I prove that you take any linear map and you can do the average, and then you get an intertwiner. Yes, for any linear map. So I fix now a linear map given by this inner product. Yeah. Yes, I start with T and then change it to no T tilde to T. No, we have T tilde is the average from T. Okay, you give me any map T and then I produce T tilde. Okay. So now I take a specific T. And then for this specific T, we know that T tilde has to be 0 because it is an intertwiner. Yeah, I'm going to do the calculation with this T tilde. Okay. So now we fix with this T tilde that we fixed, with this T we fix. So who is T tilde with this T? So let's write the definition of the T. G so what's the average applied to W2 and then against B1, okay? So say, as one can prove that if we take the inner product and the integral, actually everything is linear, so the integral goes outside, and we have this integral. Now I use the definition of T. Yes, so the definition of T was we take the inner product of this element, so we are applying, so I'm going to use another color. T of this thing, we are applying W1, so we get that we have Px, and then the inner product of rho of W2 against W1, and then the results we multiply it by some B2, and then we have against B1, okay? This was a definition of our T. So what do we have here is that I was forgetting one inner product. No, that's okay. So now, we write, so again, something like this. This is Px of B2, B1. And now I put the other inner product here. Yes. And now I variant. Yes. As I told you, assuming that the inner products are invariant. So this is the same having this inner product, and now we write W2 times rho x of W1. And now we use this inner product conjugate yeah. So there is a 2 and a 1 that this is what we call the B1, B2 of X, and this is what we call 0 of W2, W1 conjugated of X, okay? So this is actually the inner product of these two things without the X. So the of W1 and W2 are interchangeable. I had to look at the. I wanted to have W1, W2, not W2, W1. I have to check it again. We have the same thing. So we prove that we have the two non-isomorphic representations, then the inner product of this matrix of equations is 0. So they are orthogonal. Representation of the are orthogonal. So in a similar way, one proves B. Yes, and what to check? I'm not going to do this. I'm going to leave as an exercise, but I'm going to tell you something that you can do the exercise without doing a lot about it. Okay, if we take the same representation, then by sure is a multiple of the identity, okay? Given T, any map T is an intertwiner, so any intertwiner between and multiple represents is a multiple of the identity. So who is this identity? This identity is the identity we know. How do we compute the lambda? So to compute the lambda, we take the trace. Yes, we take the trace of this map, and the trace of this map will give us the lambda times the dimension of the representation. Yes. Since we are taking the average of our representation, the trace of T is the same as the trace of our map T. So lambda is the trace of our T divided the dimension of V. Yes, so this is how we get lambda, and this is why we get the dimension of V. So I go up, add all the things that are we have to compute, okay? In the case, we take the same representation. Yeah. So if we take T tilde of two vectors, say I call B4 and B2, so I have the same notation as in the statement. This is the multiple of B4 times B2, and this is the multiple of B4 times B2, and the multiple is the trace of T divided the dimension of V times B4, the trace of T divided the dimension of V times B2 D4 conjugated. So now the idea is this thing, map accordingly, yes? And the linear map that one takes is one takes V just by T of one vector is just the inner product of this against one vector that we call V3, and another vector that we call V1. Yes. So if you take this linear map, the trace of this trace of T, the evaluation of in the map, and without taking V1 data. So this, and then when we're replacing, then one gets the result, okay? So that's the idea of the exercise. We know is the following. So we go back and try to, and this statement says that if you consider matrix coefficients of representations which are not isometric coefficients are orthogonal, we get this thing. So if we get information, yes. So as a remark, we see the following: the in some books you can find the explicit formulas of what are called the orthogonal orthogonal. These are given the proof. Suppose now we can obtain all the non-isomorphic reducible representations of a group, yes? And we take all of them, okay? For each that for, yeah, with respect to the G invariant in a product. And we call this by so what we wrote before this I is and J are different, so Cij is not L, and we have an orthogonal sets in those they are so they are inside L2 functions. Okay, so we have an orthogonal set. The Peter-Weyl theorem, this is the most important theorem in, in, in this orthogonal C, dense actually are an orthogonal basis of L2G. Yeah. Because of lack of time, I cannot prove the Peter-Weyl theorem because it would take us too long. But I will tell you just the statement and some way to try to understand what is going on. Okay. So in the case of the group is finite, just the L2 functions on G are just any function because they are all integrable, all the functions, because we have the group is finite. So one see these results that actually is for finite groups. Okay, so are there any questions so far? Okay, if not, I continue. So as I told you before, we call also matrix coefficient to the functions that we define given two vectors, u and v, okay? The idea is that actually u represents an element of the dual because we are using is just the function f is just given by taking the inner product against u, okay? So another important thing or tool that we have in representations is called the character. What is the character of a representation? It's just given by taking the trace of any of all linear maps, okay? So for any x in the group, we take the linear map pi of x. This is the linear map on the vector space V. And then we take the trace, yes? And this trace gives us a number. And this number is actually could be any number, but it is called a character because it gives us a lot of information. Yes, and you will see why. So in our case, the character is given by the sum of these inner products. So this is just taking the elements of the diagonal of the matrix pi of x, okay, as any trace. So is that the characters are given by traces. So as the characters are given by traces, the character have the same value for all the elements in the same conjugacy class of G. Something that if we compute the character on a famous computer of on any conjugate of him, when this happens, we call because of the element. So as an exercise, in order to understand what are characters, I propose you the following. So if you take two representations, this map, one from D and the other from W, the character of the sum of two representations is the sum of the characters. The character of the character and the character of the tensor. In some sense, the characters, we have operation on the characters, sum, multiplication, and the conjugation, and this the sum of the characters represents the character of the direct sum. The product represents the character of the tensor product, and the conjugate represents the character of the contragradient. Yeah. So using the proof that we did above, so we go back and see. Okay, let's see. Let's take those, but the terms in the diagonal in the notation that I introduced above, this is CI, we are values of matrix coefficients. And we prove above, about before, a lot of formulas for matrix coefficients using the inner products. So if we write down this, we have following corollary. the characters form an orthonormal set. Yes. So the current representation has norm 1 and two characters of non-isomorphic representations are orthogonal. Using the formulas we have above. So again, I will show you the idea of how to prove this. Okay, so the idea that the thing is it follows directly from the formulas above. Okay, let's see how. So as I told you before, of any element x, the character is just the sum of some matrix coefficients. Yes, the matrix coefficients of the diagonal. B1, Bn is an orthonormal basis of B, okay? So who is the norm 2 of this character? This between these two, but the inner product between these two is just the sum of the inner product between the matrix coefficients. Yes. What we saw above, if we go up, so where is it? There, here, inner product between two matrix coefficients. Then we get this formula, but we took the D's that we are taking are part of our orthonormal basis. So this product is 0 if B1 is not B3 and B2 is not B4, and 1 if they are the same. So if they are the same, we get what we're looking for. It depends, they are with the, yes, so we get of the sum ij of the ij divided the dimension of B, and this is a double sum 1. Yeah. So doing the same things, we can prove B. So this leaves us an exercise. So for B, we use the item A of the proposition above, or the lemma above. Okay, so characters that seems a kind of a strange thing, they are quite useful because they are related to representations and they form an orthonormal basis of actually an orthonormal set of not basis, an orthonormal set in the set of continuous functions, and this thing will allow us to compare different representations by looking at the characters. So the first thing that we see is that we can find the multiplicity of an irreducible representations inside the other one. So what do I mean by that? So let's take any representation of a compact group. G, and let chi of B be its character, okay? So then, but what we saw today in the first part of the lecture is that this is a direct sum of irreducible representations. Yeah? So BI are irreducible. Another thing, okay, that I left as an exercise is that our character, the character of B, actually is given by the sum of these characters. Yeah, and now using the characters are orthogonal. Yes, there is a question. Yes, the dimension of B is always finite from the very beginning, from the very first lecture, because there is a theorem that I didn't prove that it would take a Hilbert, any infinite dimensional representation is a direct sum of finite dimensional ones. So we only are working with finite dimensional representations. So what was saying? Yeah. So we have this decomposition of our characters. So now we use that the characters are orthogonal. So if we compute the inner product of chi of B with a fixed uh, irreducible character, or the character of an irreducible representation, then we get ones or zero depending on the isomorphism type. So the inner product divides into the sum, and we get one every time that Vi is isomorphic to Vj, and zero otherwise. So this gives us exactly the numbers of the indices I such that Vi is isomorphic to Vj. So this is exactly the multiplicity of the I as a sub-representation of B. So this is a very important tool, because we know that any representation of a compact group can be decomposed into a sum of irreducible isomorphic or non-isomorphic between each other. So to know how many sub-representations are isomorphic to each other, we use the characters. Okay, we take the inner product of the characters, and we know that number. Yes. Okay, and even better, because in this way we know that any representation, so these numbers do not depend on the decomposition that we did above, because it only depends on the isomorphism type. So they are very good. Okay, so when we get two representations, how do we compare them? So the representations can be decomposed into a direct sum of irreducible ones. And we have different types of irreducibles inside the sum. So two representations, the multiplicity of each irreducible representation in one is the same as the multiplicity of the irreducible representation in the other. So, and how do we compute the multiplicity? By taking the inner product of the characters, so that two representations are isomorphic if and only if they have the same character. Yes? So this is a consequence of what we did before by computing the character representations contained in this representation. If two representations are isomorphic, that is invariant under isomorphisms, okay? And on the other way around, if the characters are the same, then the representations have to be isomorphic because they have the same irreducible representation as sums. Yes. So representations are isomorphic. Yeah. So it's very nice. Okay. So now it's time to state the Peter-Weyl theorem. So the Peter-Weyl theorem is dense in L2 of G. So any functions in L2 can be approximated in the norm L2, of course, by linear combinations of matrices. Yes. So to understand the functions in L2 of G, we only need to understand the matrix coefficients of the reducible representation because we can combinations. Okay. This is a very classical statement of the Peter-Weyl theorem that one can find in a lot of books. I will show you a more like modern statement of the Peter-Weyl theorem. And the advantage of this statement is that we can interpret this in a lot of things are called the Peter-Weyl theorem, which they are not actually the Peter-Weyl theorem, but it resembles the Peter-Weyl theorem because of the following. Okay, I'm going to show. So the matrix coefficients. So we check the span of matrix coefficients. So what is a matrix coefficients? As I showed you before, we take a vector in the space in V and a function in the dual, and with these two things, we define a continuous function. Yes, given by this. So in some sense, we can think about these matrix coefficients as a map taking a function in the dual space and continuous function. Yes, so we can do that for any representation. Yes, it's not necessary to be irreducible, but we can take that for any representation. So we take a representations and we look at the image of this map C, and we take all of them, and these things, the image lie inside the continuous functions. So we make the direct sum of all the images, okay? This is an infinite direct sum. And of course, what does it mean to have an infinite direct sum? That any element inside this direct sum is a finite linear combination of elements in the image, okay? So we put a name to this direct sum that is, in the literature, you can find this as O of G, yes? Or in some books, this is called C of G. It depends on the notation of the book. Maybe you will find this notation or the other one. Yeah. So this is space. But since the group is compact, one can only take the reducible elements. Yes. In modern terms, this the idea is this one can construct this object in any category of representations having tensor products and duals. Yeah, this is all the things that we are looking. And with some, and of course we need direct sums. If we have all these three ingredients, we can define this element, and this element is called the coend of the category. So, and this element is called the coend. Yes. And the Peter-Wald theorem reads that if we complete, so we take the L2 norm and make a completion of this object, then we get L2. Yes. So a lot of people says that we have a Peter-Wald theorem by constructing the end like this, but this is not actually the Peter-Wald theorem. The Peter-Wald theorem is what is below, okay? But it is called the Peter-Wald theorem, but it's not actually the Peter-Wald theorem. Okay, if as I told you before, is if the group is fine, L2 algebra of functions of O of G and the algebra of functions on the group, and this is on one hand, but on the other hand, all the vector spaces given by this is what one learns in linear algebra, I hope. Sometimes sometimes no, it depends on who is teaching linear algebra. Only of the vector space V, which are, by fixing a basis, just a matrix algebra, yes? So the decomposition given by this star is another way of finding the famous theorem of Wedderburn, that any simple algebra is the direct sum of matrix algebras, okay? So we find the Wedderburn theorem here as a consequence of what we are doing for finite groups, yes? For compact groups, it is not the Wedderburn theorem because they are not semi-simple, because we may have infinite irreducible representations, yes? And to finish the course, we are going to see the representations of SU2 actually infinite. They are infinite ones. Yes. So product coinversion of the Peter-Wald, yes. Each V appears once. Yes. Yes, because actually any representations is the sum of the direct sum of irreducible ones, and then yeah, like you put the multiple of the one if appears more than once, the multiplicity. It has to do with the fusion rules of tension of the sum of irreducible ones. The Yes, but yeah, what I'm saying is that the V that appears once appears and V star tensor V. The V appears once. So this is the matrix algebra, or in terms of compose the irregular representations. Every representations appear once, and the times that it appears is the dimension of the representation. And this is actually another way of saying that one have the V tensor V, write this here. So in finite groups, we have something like this. Appears 1 times the dimension for V irreducible. Yes, and this is actually represented by this thing, okay? This is what is happening. Only once. If we look at as representations, then of course it appears dimension of B times, yes, because it is given by this thing. I have negative time, so I'm trying to give you the ideas of how can we produce, how can we describe representation of a concrete group. So SU2 is the set of unitary matrix of 2 by 2. So we want to describe the reducible representation of SU2. These are very important in physics. So they have names. Right? So how to find the reducible representation? So we use a lot the unitary group, which is given by the circular group. The circular group can be seen inside the unitary group by taking the. So since the matrix has to be unitary, we take diagonal matrices since they have and set -1 in the diagonal, and the set has to have modulus 1 because we are in the unitary group. Okay, so one way, there are a lot of ways of defining the reducible representations. Now, okay, as follows. We take the linear space of polynomials, homogeneous polynomials of degree n in two variables. So, for example, for n equals 0, we have the field. For n equal 1 is just the relations of the two elements x and y. For B2 are the linear combinations of these monomials, and so on. So for these spaces, we define an action of SU2 by a matrix. So how do we define the action? So we take a polynomial, any polynomial, these two variables homogeneous, and we multiply by a matrix on the right. So we think as this x and y to be rows. We multiply on the right, and we get, again, a row like this, and then we evaluate the polynomial. Yes? So in some sense, we are acting on a dual space of something because we're acting on polynomials. So we act on what is evaluated in the polynomial. Yes? And this evaluation is given, we have to put the inverse there because this is how I define the contravariant representation. But the idea is, okay, we don't do that. We put the action on the right, which is isomorphic, and then we take the rows. So in this sense, one can prove that if we do that, for n equals 0, we get the trivial representation. So the trivial representation will be there, is irreducible. And for n1, we get, as I told you before, the dual representation of the sum, which is here, and on and so on. We get a lot of the representations are all irreducible. So I will show you a sketch. Then in my notes, they're going to see more or less the whole proof now in the sketch. So I'm already late. So how do we prove that it is irreducible? So the first thing that we do is, okay, we look at the action of T on the basis. The basis of the homogeneous element is given by these elements, okay? So from 0, k to n. So we look at the action of T on these elements, and one can prove that for any matrix like this, acting on, say, pk, so let's call this pk. This is a multiple of this set given in the diagonal matrix. So this is set to the n minus 2k x n minus k yk. Yes, so it is a scalar. So all these monomials are one-dimensional for their circle. So in terms, all the weights. Yeah. So the thing is, the n an invariant subspace